Good morning and welcome to Advent of Code in F# day 16 already. As always, before we start with today's puzzle, I wanted to quickly come back to something from yesterday. So yesterday was the numbers game the elves played. And I solved it by generating the infinite sequence of numbers and then grabbing the 2020th number that we were looking for. And I used something like this, the generate sequence function here. It's an infinitely recursive function that just always returns the next number, and it keeps going. I had a good night's sleep on it, and actually this is literally an unfold. We used it in one of the examples in the past, but if you want to generate a sequence from an initial state and you have some calculating function, you can always use you can use an unfold. So this was a refactoring I did for yesterday. I did some playing around with the big input and it's a bit slower, but it looked way cleaner, so I refactored it anyway. But without further ado, let's go take a look at day 16. Ticket translation. So we're still not at our destination and we're still traveling. One of the legs of our rerouted trip coming up is on a high-speed train. However, the train ticket you were given is in a language you don't understand. Interesting. Should probably figure out what it says before you get to the train station after the next flight. You can't actually read the words on the ticket. You can, however, read the numbers, and so you figure out the fields these tickets must have and the valid ranges for values. Oh, that's an interesting problem. We collect the rules for ticket fields, the number on your ticket, and the numbers on the nearby tickets for the same train service via the security cameras. That's safe. Together into a single document you can reference, which is our puzzle input. Let's just take a quick peek. Ooh, let's see. A lot of parsing that's going to happen here today. Grab it, paste it. Whoa. Okay. So we have a bunch of input. Where were we? Yeah, so we have our puzzle input, which is a lot of information. The rules for ticket fields specify a list of fields that exist somewhere on the ticket. So we have rules for ticket fields, and we're not given where they are. They're just somewhere, and these are the valid ranges. So class should be between 1 and 3 or 5 or 7. Oh, there's ors in there. Will today be the day we write an actual parser and not just a regular expression thing? If today's solution lends itself to it, I'm gonna use a parsing library to mix things up. So yeah, we get validation rules for fields somewhere on the ticket. Clear. Inclusive, yes, okay. Each ticket is represented by a single line of comma separated values. Okay, so every line in the input after the rules are tickets. The values are the numbers on the ticket in the order in which they appear. Okay. Every ticket has the same format. Okay. Question marks is whatever the field names are in the language we don't understand. This ticket might be represented as left to right, top down listing of all the numbers. Yep. The actual train tickets you're looking at are much more complicated, of course. Okay, so we don't know what the index means, which field it is, but we do know it's one of the fields. Oh, I see where this is going. So start by determining which tickets are completely invalid. These are tickets that contain values which aren't valid for any field. So when we see a value that doesn't match for any of the rules, that's what we have to do in part 1. So for example, field class has this rule, row and seat, and then we have one ticket and nearby tickets. Yeah. It doesn't matter which position corresponds to which field. You can identify invalid nearby tickets, so not ours, by considering only whether tickets contain values that are not valid for any field. So okay, so yeah, we have number 4 4 is not valid for any of the 3 fields, so we can invalidate this entire ticket. That's clear. And adding together all of the invalid values. What? So in this example, the values on the first nearby ticket are valid. This is not true for the other 3 nearby tickets. The values 4, 55, and 12 are not valid. So you need to count or sum up the fields that we find that don't apply to any rule, or where all rules are like invalid. Yes, okay. And we only need to look at the nearby tickets. And the scanning error rate is the sum. Okay, that's clear. Should we use the small example? I think we should. So the only thing that's a bit special is or. Let's take a look. Is it always or? Yeah, there's no and, there's no not. It's not more complicated than or. Forget I said anything about a parser library. We can do this using everything we've seen up until now. Let me pull in the example. I don't know why I put the input in a file and the example in a string, but that's just me. Let's roll with it. Let's split on a new line. Come on, you know you want to. Okay, sorry for that. So let's split on a new line. Come on, IDE, work with me here. So this should be the lines. Last row, yep. Let's keep track of the new lines. Let's not throw them away, so we can easily identify when we stopped processing rules, when our ticket enters the show, and when the nearby tickets start to go. Yeah. No, actually, that's not necessary. No, that's not necessary. So let's remove the empty lines. Okay, first things first, let's do a bit of parsing. It's not really the most productive thing to do if you're doing this like for fastest, for speed solving, but we're not doing this for speed, we're doing this for fun. So this is a list of strings now, yeah, or an array of strings. Let's group it into the rules, our ticket number, and the nearby ticket numbers. So for the rules, let's extract the rules first. So we just take while we don't see this line, or there's tabs in there. I don't think it will enjoy tabs in there. Okay, I just convinced myself to pull this into a file. Always keep your tests as relevant to production or the real thing as you can. Otherwise you're fighting with new line inconsistencies and stuff like that. So actually we can do the same as we would for a real input, just read a file. There we go. And it's the example. And let's read all the lines instead of everything as a single string. So now we're back where we were. Yes, there's new blank spaces in there. Let's get rid of that here. Yeah, let's write a parse function. The parse function will come here, and then we'll clean up the no empty lines. I know it's fun, but fun capital L F might be a bit of overkill. So let's remove the empty lines. I'm still tracking times for some reason. There we go. So rules is everything until we see, what was it? Your ticket. So this should be the sequence of rules. What do we have? What do we have? 1, 2, 3 rules. Is that correct? Yes. And then we have your ticket. So let our ticket yeah, it's not that big. Let's just keep going with take whiles and skips. Let's skip as many lines as we have rules. Our ticket is now our ticket. Oh yeah, there's the your ticket line in there as well. So we can ignore that line. Oh, come on. 7,114, is that correct? Yes. And let's just take the first element. That's our ticket string. Yeah, that's our ticket string. Let's keep that a string for now. Okay. And what's the next thing? The nearby tickets. So skip while. Is this not something you can do? Like without typing the font? Yeah, this is something you can do. So nearby tickets is now the thing we need to find. And the first one we see is 7347. Okay, skip while takes the line, so we can skip the line itself and end up with all the tickets. How are we going to represent the tickets? I think for now just a list is fine. Let's make that explicit by providing a typed alias. So tickets are lists of ints. Our ticket is a string. Let's write a parser for a single ticket. So text is a string, and text dot split on comma, and everything is an int, and let's make that a list instead of a lazy sequence. So that's our ticket parser. Let's use that to parse our own ticket, and let's use that to parse every ticket in here. And let's also make that a list. So yes, that looks correct. And the rules, what are we going to do with the rules? Do they always have or? No, they don't. In the example they do. In the real world they don't. Do they? Oh, they do. There's always a or. Every line, yeah, every line is colored. Okay, so it's even, so it's pretty straightforward. Yes, let's use regexes, because we've been using regexes for every kind of parse. That's non-trivial, so let's go. This is the line we need to match. So we need to extract the what's it called? The field name, and then this, and then digits, and then a minus, and then some more digits, and then or. It's always there. I think this is our thing, and all the groups, like all the parentheses are groups, so we can read out we can read out the rule. So let's write a parser for a rule. I'm not going to use the type provider. I'm just going to use regexes, plain and simple. So open, where are they at? Text, regular expressions, yes. Let's load them in the REPL, go. What's the regex like? Our rule regex is a regex with this pattern. Okay, let's just play around with it. It's one rule, so we just need to match, yeah. Let's play around with the given example. What's the easiest way to represent a rule? It's just a field name and two ranges, like from to. Let's just keep that as a record type, which has the field name, and the ranges is just a list of pairs. Yeah, why not? So from, until, and let's keep several of those. There's always two, but this might make it a bit easier to work with it. So what do we need? The field name. So is it groups or captures? It's groups. Let's see, this should be the field name. No. Yes, maybe. This is the field name, yeah. And then we need the four ranges, which are in here. So first lower bound, it's a very cryptic abbreviation. Yeah, and let's parse that as an int as well. It is already an int? No, that can be the case. Value, dot value, sorry. And that can be an int. Yeah, okay, so I think this is our basic structure. Let's wrap it in a function. Didn't we have a function? Nope. Oh yeah, we have it down there. So parsing a rule is using this regex, matching and extracting the fields, and then returning a rule. But let's just first do the all bounds. So it's the first lower, the first upper, the second lower, the second upper. Yeah, let's go with it. And what was the thing? Ranges. And ranges are the first lower, the first upper, and the second lower, second upper. So this parses a rule. This is our example, but we kind of want to use this for every line. So here we go. Whenever I do something I'm not 200% sure of, let's drop to a test. Let's try to parse this rule. And that looks correctish. Let's verify the ranges. The partial location, yes, 37,479. Yeah, 485, 954. Okay, that looks good. We can parse tickets. Can we parse everything in the example? Yes, we can. Okay, so this is a parser. Let's wrap it in a function because we're going to need it for real. So, I like my types. I don't know why, but I like my types. So we need the rules. We need the ticket. And we need the nearby tickets. Right. So let's fill it in. There we go. So if everything lines up, let's make everything a list because that's easier to work with. I think we have our parser ready. No, what's wrong with rules? We are not parsing our rules. That is correct. Now we are parsing our rules. So, okay. I think we're done with parsing. Quick sanity check, 7114. Couple of tickets. Yeah. The rules are class, row, indeed, seed. Yeah, looks good. So for the first part, we need to find all the fields and nearby tickets where none of the rules apply. So for parsed dot nearby tickets, we need to apply the rules for every field. So I'm just going to do collect every field. So this is flattening every ticket is a list of numbers, and this is just like concatenating all the numbers into one bigger sequence of numbers. So containing all the fields of all the passwords. For part 2, this will probably be bad idea, but for part 1, we're good. And now we just need to find the invalid numbers, or the numbers for which no rules apply, and then sum those up. So we need a filter. Field, so the field is valid not, and then let's just sum those up. So yeah, let's write the isValid function. So this should return this should take the rules. It's pretty important. And the field, so isValid takes the rules and a field, which is in our case just the number, not the entire ticket. Yep. And let's have it return true or false. Let's clean this up a bit. So collect every number, yes. Filter, yes. And sum. Is this correct? Yeah, so the not valid numbers given the rules. Okay. Is valid. So we look for every, or there must be at least one rule where this number falls into, or let's call this a number, where the number falls into one of the ranges. So rules, there must exist at least one, yes. One rule where the rule applies to the number. Let's extract this again. Applies rule number, and rule is a rule. So we're just breaking down the problem into smaller steps, and now I think we're at rock bottom. So rule has a field, which is not important for us. The ranges are, let's go again. So there must be a range where our number is within the range. So what was range? A tuple or a pair? Yeah. So min, max, max. I'm even typing things in reverse order. So number should be between and, yeah, and. So it should be between, and I thought the ranges were inclusive, sorry. So I think this is enough for part 1. Let's give the example to it, 71. 71, that looks correct. So let's run on our input. Interesting. Come again. I can parse my oh yeah, I had a different read function, so let's try it again. Yes, we can parse our input. That's always a good start. And we have a bigger number, which might be our correct answer. Yep, we're good. Part 2, part 2. Never think about part 1 again when you move to part 2. That's my strategy. So here we go. Now, what's part 2 about? Okay, we can get rid of these tickets entirely and use the remaining tickets to determine which is which. Interesting. I love it. This is a cool part 2. So we can throw away the tickets we invalidated here and start working from there, and then we need to derive the which number represents which field. Cool. That's a cool search problem. So using the valid ranges for each field, determine what order the fields appear on the tickets. The order is consistent between all tickets. Yep. If seed is the third field, it is the third field on every ticket. That makes sense. Suppose you have the following notes. Is this the same? Oh, why you change examples? So no, it's not the same. Suppose we have the following notes. Based on the nearby tickets, the first position must be 3, 15, or 5. 3, 15, or 5. Yeah, 3 does not match. 15 does not match. Yeah, okay, makes sense. Huh. This is like a... How will we approach this? And then we need to look for the 6 fields on our ticket that start with the word departure. Do we have 6 fields with the word departure? This is so bright for my eyes this early in the morning. Oh yeah, so it's just the first 6 rules for me. We need to find the values on my ticket for these rules. And then multiply those to get a number. Yeah, okay. So every ticket has the same structure. So for each of these 3 indices, we need to find the correct rule so that all the valid tickets are... Yeah, so the rules apply for all the valid tickets. That's an interesting problem. Yeah. I'm gonna let that percolate for a while and let the caffeine kick in a bit. But the first thing we can do is get rid of the invalid tickets. So instead of dumping every number of a ticket into a single list, let's not do that anymore. And let's write our validation on ticket level. So now isValid takes a ticket. Applies R on the ticket. And what does it mean if a rule applies on a ticket? That means that for every ticket, a rule must be valid, right? Right. So for every ticket, for every field on a ticket, yeah, so for every field on a ticket, or for every number in a ticket, let's go like that. Don't need to change that much. And there we go. I think this will work, and this will filter our invalid tickets. So if we remove the not, we should end up with valid tickets. Ooh, this feels uncomfortable because so these are the nearby tickets that are valid. So we're changing part 1 up a bit, and we have no way of really validating whether this refactoring or this tweak work correctly. Can we figure it out for the... We can figure it out for the easy example. So it's there's only one valid ticket in the example. No. Great. So there's a bug. Good thing we did this before we started continuing on. So we have rules, our tickets, and we have 1, 2, 3, 4 tickets. And actually the first one, yeah, the first one should be valid, right? 7347. First one should be valid. Yeah, let's just try it out. Is valid parsed rules for the first ticket. Let's see what change we made that broke this. What's going on here? It's not valid, but it should be valid. What's the problem? Yeah. So we changed up a bit, and here, yeah, this can work after we parsed it, or before we parsed it. I think I already see the problem. We're looping over the rules, but actually we need to validate every number. So we need to say the same thing as we did above, like for every number in a ticket. This is a bit of a roundabout way because we won't be needing this. Yeah, we will be needing this. Okay. So for every number in the ticket, this must apply. There must be a rule. Yeah. So there must be a rule that applies to the number. Oh, that's actually what we were doing here, right? Yeah. So actually this is, there must be what? No. No, that's correct. I'm losing my way here. So actually what I'm trying to say here is actually just applies yeah, no. So we still need to do something for every number. So this is still a I think it's more something like this. And then the rule. There should be a rule where the rule applies to the number. So this is wrong. We can actually do that for part 1 at least, or for filtering the invalid out of there. So this makes more sense. So when is a ticket valid? Well, if for every, or for part 1 at least, if for every number we have a rule that applies. Yeah. So are you correct now, dear ticket? Yeah, it's correct now. So if we do this now, we should have a single new valid ticket. Yeah, okay, we're good. Whew, glad we pulled that bug out of the code before we continued on, because that would have been a rabbit hole, a very deep rabbit hole. So we can end up with the valid nearby tickets. Let's quickly grab the second example so we stay relevant and we start looking at the same numbers. Let's just do a new example. And let's parse in example part 2 instead. And let's fill that file with our new input, which is 11, 12, 13, right, okay. Let's see if we can still parse. We can. Do we know stuff? We know that there's no invalid in there. So there should be 3 valid nearby tickets. 1, 2, 3, yeah. Or that was an assumption, but appears to be a safe assumption. Okay, so we have our valid tickets, and now we need to figure out which rule applies for which field or for which index in the ticket list. How will we do this? If we had Prolog, we could be using its native backtracking algorithm. Could we? What's a smart approach? How many tickets do we have? Quite a bit, 200-ish. I'm thinking, like, would a naive just try to find a single rule that is like 100% sure, so that we don't have to do a bit heuristic searches or too much of backtracking? Interesting problem. How would a human being solve this? So how would I solve this? We see a set of rules and we see a set of numbers. And we should base ourselves on the nearby tickets, so not including our own ticket. What would be the naive approach, or like the simplest thing that could possibly work? Just take a look at every rule individually? No. Let's take a look at every index individually. Yeah. And let's try to just apply every rule. And if there's only one rule that hits, then we're 100% sure that that is the rule for that column or that part of the ticket. That sounds like an expensive way of doing things, but I'm gonna first try that, and if my computer doesn't blow up, then I will be a very happy camper, or a happy Christmas elf. So loop over every index. Let's try it with the first index before we go too deep into do it for everything. So for the first index, we need to collect every value for that field. So those are in valid nearby tickets. So valid nearby tickets, let's take the first number. So this is the first number of every ticket, 3, 15, 5. Yep. Is the first one a simple one? Is there only one rule that applies for the first one? 3, 3, 3, 3, 15 and 5. 3 and 5 match here, 3 and 5 match here, but 15 doesn't match here. So yeah, that will work for our example. So these are all the values that a certain position in the ticket has, and let's figure out how many rules could apply. So parsed rules. Let's figure out how many apply. Yeah. Or let's keep the ones that do apply. So it's a filter. So the rule applies to all the values. Do we have applies? We have applies. Let's use our applies. That's still valid, right? Yeah, that's still valid. But then instead of values, it must be for every value. Is that exactly the same as is valid? Yeah, in a sense. Other than the definition of tickets, that's a let's not call this ticket, let's call it numbers. And I think this is exactly what we need then. So for every number, there must be a rule. No, that's not what we need. We need the rule. So, okay, let's not reuse this, but let's reuse our applies. So applies takes a rule and a value. And we have several values, and it must be for all the values. So values for all values, the rule must apply. And these are the rules we're sure about. Let's call those matching rules or passing rules. So these are all the rules that for the first field have a match. And it's funny because it's saying we have unmatched parentheses. So no match. There we go, match. And it's the row. That's correct. But in order to generalize this or to make this the core of our search algorithm, I don't think we can assume that we will find a single matching rule going left to right. So what if instead of going left to right and always assuming that there will be a single matching rule or passing rule, what if we do this going left to right and we try it until we find a field or an index where we have a single rule? If we have none, we have a problem. But if we have more, we can't be too sure, and we should be like in a backtracking thing. But let's not do that right now. Let's first just make the assumption that there will always be a field that we haven't visited yet, that for which a single rule applies. That's a slippery assumption that might not be correct, but then we'll see the error clearly in our face in just a second. So strategy, just find a next field where we have a single rule, and if we do, cool, we like check that index until we're done. And done means all the rules have been used up. We have like 3 fields, we have 3 rules, I think so. So we can do this until the rule set is empty, or until every rule has been assigned to a column or an index. Yeah, let's try that. Rules for fields. Come on, I can type. I know, okay. So let's write a recursive function. Yeah, why not? Given rules and all the tickets, we can do something. Let's first do a match on the rules. If we have no rules, then we're done, right? Yeah, I don't know what done looks like, so I'm just returning an empty list. Otherwise, we have rules, and then we can do this, but not only for the first element, but for the first element where a single rule gets returned. So let's extract this. What are we doing? So for an element, find all the passing rules. For an, let's not call it element, but index. So for an index, let's find the passing rules. And that's this thing. So let's grab it and put it in here. And it's saying, so select nearby tickets. No, no, no. Yes, we also need the tickets. Let's put in the tickets as well. Yeah, let's put in the tickets as well. So grab the not the first element, but the indexed element. Let's find all the rules. Let's find all the rules, and if there's a single one, if there's a single rule in the passing rules, we found it. So let's just use an option type saying, yep, this is the rule you're looking for. What's wrong? I could use a list. Yeah, sure, I could use a list. And it's not fitting on my screen, so I'm just gonna format it a bit. There we go. So if we find a single rule, we're done. If we don't, whatever. If we find no rules, we have a problem. Yeah, let's make that explicit. No rule for a column index is a major problem, so what's this string interpolation thing? Yeah, let's use string interpolation. This is a new feature in F#5, so it's not in my fingers yet. It's something that's been in C# for years, so I don't know why I'm having this much trouble with it. So no rules is a big problem, because then we exhausted our search base. If the assumption doesn't hold and we need to backtrack, then we need to be a bit smarter about this edge case. And otherwise, we found multiple rules, and multiple rules are not good enough for us. So we're doing a naive, or are we doing a brute force? We're doing a brute force. It was saying that nth, the function nth is deprecated. Interesting. So we're doing a brute force search, just trying every index, and if we find something cool, we can check that off, and otherwise we try another one. So it's not the most performant search, but I'm guessing it'll work. So this thing gives us a single rule, if there is one, for an index in all the tickets. I think we can use this. Yeah. So what do we need to do? Yeah, and then we need to loop over the indexes. Yeah, we're still good. So no rules, we're done. Here in this case, we have rules. What do we do? Then we find the first rule. No, we find the first index where a single rule matches. So we need the indices that still need work. Otherwise, we will be doing a lot of duplicate work. You know? I was thinking like, okay, always keep looping over the rules. But if we do that, we're going to be revisiting all the indices of rules that have already been matched. So maybe rules is not the best way. Maybe indices is the best way to structure our algorithm around. So if we have no more indices to visit, then we are done. Otherwise, yeah, then we can just take the first index, because we're doing let's find the first index for which we have a single rule. So let's do that. So indices, and let's what's it called? Choose pick. There's a function that works with something that returns an option and returns a single value. So I think it's pick. What's the difference with choose? It returns a list. Nope, we need the first one, so that's pick. So for every index, pick the first one that has this function return sum. So indices, pick the index where find passing rules for rules given are tickets and the index. But if the last argument is like your function or your lambda input argument, you can just move that out. So this is the first index for which we have a rule. And we kind of also need the index, because right now we're just yeah, let's make it easy on us. Let's return the index and the rule, just like this. it needs to be in parentheses because otherwise our compiler can't follow, or it's incorrect syntax, or it means something else. So this is the index and the rule, or the first index for which we have a single rule. So this can all go. And I'm assuming it always finds something. It could be that it's not and that we have to do some backtracking, but we're ignoring that possibility for now. So this is actually what we need. So this index matches this rule. And so no tail recursion just yet. Now we can work recursively by looking for the rules for fields. But indices, we can nibble off the current one we found. So the index we just found, we don't need to look at that anymore. And actually we can also discard the rule we just found. Cool. So rules except the current matching rule also. And tickets remain the same. Yeah, I think we're there. What's happening? What's happening down here? Is this like not a complete statement? No, it's not a complete statement. We're missing parentheses somewhere. Oh yeah, there was one missing. What's the problem here? Rules, except the rule. Sometimes it's a good thing to have a type checker in strong types. Okay, this is the naive approach. Let's take out where are valid tickets? Where are valid tickets at? Oh, this was the thing I was looking for. Yeah, we still need that actually. So, okay, we did a lot of hypothesis or like imaginary programming without getting feedback. So let's get some feedback again. Okay, we have our parse thing, we have our nearby tickets, and now let's try to find rules, fields. Oh yeah, we need the indices. So that is actually, let's do that on parsed dot our ticket. That's the ticket, and we need the indices. So it's this is not the most ideal way, but let's make an index list. Let's take the indices. It works. It works. Yeah, it works. I could just have like generated a sequence from 0 to the length, but that's boring, right? So then we call our search algorithm with the indices, with the rules, which is in the parse result, and all the tickets, which in this case are only the valid tickets. There we go. And we crash hard. No. Oh no, does the naive approach not even work for the example? Are you kidding me? What? Line 65? An index satisfying a predicate was not found. Let's clear everything up. I'm confused by the error line. Maybe this is some kind of F-sharp interactive thing, but I'm confused. We actually even have a compiler error that explains. Yeah, this is not something we want in there. Oh, there we go. So actually we do have it working for the basic example. The first column is row, the second is class, and then we have seat. Is that correct? Row, class, and seat. Yes. Now I am hoping this works for a bigger input, otherwise our search algorithm needs to be smarter, or it needs to incorporate a bit of heuristic and backtracking. But let's worry about that when we need to. Let's not worry too soon. That's a bigger search space, all right. Oh, the naive algorithm works. Okay, so we have the rules for every column. And what do we need? Look for 6 fields on your ticket that starts with the word departure. What do you get if you multiply those 6 values together? So we need to get the 6 indices for the departure rules. So let's grab those. So it's index and rule, and we need one where rule field starts with departure, right? Yeah, so this should be 6. 1, 2, 3, 4. Yeah, probably. No, not probably. We don't deal in hypotheticals here. Okay, so these are the 6 we need, and let's take the. Why am I always dropping to sequence when I know it's a list? I don't know, but it's a bad habit. I don't know if it's a bad habit, but let's grab the indices. Indices are the first in this tuple. There we go. So these are the indices for departures, and let's grab these out of our tickets. So for every of these indices, let's grab the index from our ticket, which is in the parsed result, our ticket, the ith element, and what do we need to do? Multiply these 6 values. So multiplication of a list we can do with the reduce, sure, why not? There we go. Let's see if everything worked out nicely today. No, dear. It looks like it's overflowing, but let's take a look at those numbers. Is it just a problem in the... Yeah, so let's map these to something that will not overflow to a long. And if we multiply now, yeah, that's a bigger number. Here we go. There we go. Yeah, fun puzzle. A bit disappointed that the naive algorithm works, that we didn't have to do backtracking or heuristic searches. But for 1 hour of effort, that's good enough for a mid-week puzzle. So hope you had fun, and I'll see you tomorrow for the next Advent of Code in F#. Bye bye.